We'll start off this algebra segment by taking a look at integer exponents. In fact, we'll initially assume that the exponents are positive, and afterwards we'll also tackle integer exponents which are 0 or negative. Let's first recall what an integer is. An integer is a positive or negative whole number that does not have a fraction or decimal part. So examples could be -5, -4, 0, 1, 2, and so on. Whereas examples of non-integers look like -0.3, 3.7, 1/2, and so on. Let's next recall the definition of exponentiation. With positive integer exponents, we'll say that if a is any number and n is a positive integer, then a to the power of n is a times itself nth amount of times. So for the example we have here, 2 to the power of 3, where 2 is a number and 3 is a positive integer, we have 2 times itself 3 times, which is 2 times 2 times 2, which equals 8. This is also a good moment to review how parentheses are used in exponentiation, and the standard conventions that govern them, especially since the rules become crucial when dealing with negative numbers. So let's consider two cases. We'll have -3 to the power of 2, and we'll also have -3 to the power of 2. These will have different values once we evaluate them. When performing exponentiation, we have to remember that it is only the quantity that is immediately to the left of the exponent that gets the power. So in the first case, there is a parentheses immediately to the left, so that means that everything in the parentheses, namely -3, gets the power. And so we get -3 times -3, which is just 9. Whereas in the second case, the 3 is immediately to the left of the exponent. The minus sign will stay in front and will not get the power, and so we get -3 times 3, which is -9. And to remove the brackets or parentheses, it is just -9. Now let's take care of zero exponents and negative integer exponents. In the case of a zero exponent, we have a to the power of 0 equals 1 for all a that is not 0, since if we had 0 to the power of 0, that's not well defined. So for an example, let's say we have -400 to the power of 0. That's just going to be 1. Again, provided that -400 is not 0, which of course it isn't. Now in the case of negative integer exponents, we have a to the power of -n equals 1 over a. Again, this is provided that a is a non-zero number, since division by 0 is not well defined. And n in this case has to be a positive integer, since if n was also negative, then -n would become a positive integer, and we'd be back to working with positive integer exponent rules. Now for a quick example, let's take -4 to the power of -3, which equals 1 over -4 cubed, which is just 1 over -64. We'll take a look at something more complicated after looking at the general properties for integer exponents. And so feel free to pause at any time to digest them, and hopefully they feel pretty intuitive. So for the first property, we have that if two of the same bases are multiplied with different integer exponents, then that is equal to that base to the power of both integer exponents added. So for example, let's say here we have a to the power of -5 multiplied by a to the power of 2, then that's the same as saying a to the power of -5 plus 2, which is simplified down to a to the power of -3. So for our second property, we have it that if a to the power of n is inside the parentheses, and outside of the parentheses we have to the power of m, then we'll say that that is the same as a to the power of n times m. So in the example, if inside the parentheses we have a to the power of 7, then outside the parentheses the power is 3, then that's the same as a to the power of 7 times 3, which is a to the power of 21. Next, we'll give a piecewise definition where we have a to the power of n over a to the power of m is just the same as a to the power of n minus m, where n is greater than or equal to m, and if n is strictly less than m, we'll say that a to the power of n over a to the power of m is 1 over a to the power of m minus m, all provided that a is not 0. So to look at examples, because this may look scary, we'll give cases for both. So a to the power of 5 over a to the power of 2 is the same as a to the power of 5 minus 2, which is just the same as a to the power of 3. And with the same case, let's look at the bottom part of the piecewise. So a to the power of 5 over a to the power of 2 is the same as 1 over a to the power of 2 minus 5, since in this case we're doing n minus m, and in the latter case we're doing m minus n. And so this is the same as 1 over a to the power of negative 3, which is just a to the power of 3. And as you see, they yield the same result. Next property is that if inside the brackets we have a times b, and that's all to the power of n, then we'll say that that's the same as a to the power of n times b to the power of n. So for an example, we have in the brackets ab all to the power of negative 4. We'll then say that that's the same as a to the power of negative 4 and b to the power of negative 4. Note that this was only given with two factors, ab. However, it can be extended to, let's say, a, B, C, D, E, all to the power of n, and this rule would still hold. And quite similarly for quotients, we'll say that inside the brackets, if a is divided by b, all to the power of n, then that's the same as saying we have a to the power of n divided by b to the power of n, provided that b is not 0, since we can't divide by 0. With the example, a divided by b, all inside the brackets, to the power of 2, that's the same as saying a to the power of 2 divided by b to the power of 2. Now, following from the previous property, if all we did was make n a negative integer, then we would have inside the brackets if a was divided by b, all to the power of negative n, then we just swap the denominator with the numerator, a over b to b over a, then we just remove the negative sign from the integer exponent. And then from one of the previous properties, we could see that that becomes very quickly b to the power of n over a to the power of n. So with the example, if we have a over b all inside the brackets, to the power of negative 2, then that's the same as saying we have all in the brackets b over a to the power of 2, which becomes b to the power of 2 over a to the power of 2. Our seventh property is saying that if inside the brackets we have a product of a and b, and that's all to the power of negative n, then we'll say that that's the same as saying 1 over inside the brackets a times b all to the power of n. So with the example, we have inside the brackets a times b all to the power of negative 20, then that's just going to be written as 1 over inside brackets a times b to the power of 20. Now, if you notice, all we did there was give b a coefficient of a. In all the cases with negative integer exponents still hold. Our eighth property is saying that if we have 1 over a to the power of negative n, then that's the same as a to the power of n, which you may have noticed in the second example for our third piecewise property, where if we have 1 over a to the power of negative 3, then that's the same as a to the power of 3. Now, if you intuit that, then you should be able to understand that if a to the power of negative n is divided by b to the power of negative m, then that's the same as b to the power of m over a to the power of n. So for example, if we have 2 to the power of negative 3, all divided by b to the power of negative 2, then that's the same as 5 squared over 2 cubed, which is 25 over 8 upon simplification, which is good practice for later. Now, the last two properties left may look scary, but they're very easy to recall once understood, so let's check them out. So first we have, if inside the brackets it's a to the power of n times b to the power of m, all to the power of k, then that's the same as a to the power of n times k multiplied by b to the power of m times k. So for example, if we have a to the power of 4 times b to the power of negative 9 all inside the brackets, all to the power of 3, then that's the same as saying a to the power of 4 times 3 times b to the power of negative 9 times 3, which is all when simplified a to the power of 12 times b to the power of negative 27. Now, if you've noticed, this property is just a combination of our second and fourth properties. For our final property, if we have a to the power of n divided by b to the power of m all to the power of k, then that's the same as saying we have a to the power of n times k divided by b to the power of m times k. So for example, if we have inside the brackets a to the power of 6 divided by b to the power of 5, all to the power of 2, and that's the same as saying a to the power of 12 divided by b to the power of 10 upon simplification. Now be aware, this doesn't get us anything about subtracting the two exponents because a and b aren't guaranteed to be the same. So for those who forgot our first property, if we have a to the power of b and then a to the power of c, then that's the same as saying a to the power of b minus c. Now that was quite a mouthful of properties to recall, but thankfully that won't be the case very often in this algebra segment. So let's turn to some common mistakes that I see with respect to these properties. So let's consider the case of a times b to the power of negative 2. So the correct equality would be a times 1 over b squared, which when simplified is just a over b squared. Now, what a times b to the power of negative 2 wouldn't be equal to is 1 over ab squared. Because remember that when dealing with integer exponents, only the b in the exponent gets the power, since it's immediately to the left of the exponent, and so only that factor moves to the denominator, whereas a should actually go to the numerator. Now, in contrast to the case of inside the brackets, we have a times b all to the power of -2, then we would in fact get 1 over ab to the power of 2. So it'd be good to note the importance of parentheses for exponentiation, as I mentioned before. Let's look at one more common mistake I see very often, and then we'll end on some practice examples for you to tackle. Now, in this case, only a has the exponent. And so to use property 8 on this, we'd have to break up the fraction as shown, and then use property 8 only on the second term. Now, if we wanted to bring the 3 up, we would need something like 1 over 3a to the power of -5, which would then give us 3a to the power of 5. Again, important notice of how parentheses can change the equations. To end off, I'd like you to pause the video and simplify each of the following and write your final answers in positive exponential form. Let's now walk through them, and I advise that you watch this part just in case. You may have gotten the right answer, but for the wrong reasons. So for a, since the numerator and denominator have the same base, we can just simply subtract their exponents. So we would get x to the power of 8 minus 3, which is just x to the power of 5. And now if this was written as x to the power of 3 over x to the power of 8, we would do the same thing. That just becomes x to the power of 3 minus 8, which is x to the power of -5. However, this is not written in a positive exponential form, so we would have to rewrite this as 1 over x to the power of 5. So now for b, first we can simplify the coefficients. So we know that 4 divided by 2 is 2. And now we can simplify the powers of a. So a to the power of -2 over a to the power of 1 is the same as a to the power of -2 minus 1, which is a to the power of -3. Now we can simplify the powers of b. So b to the power of 5 over b to the power of -3 is b to the power of 5 minus 3, which is b to the power of 5 plus 3, which is b to the power of 8. And that gives us 2 times a to the power of -3 times b to the power of 8. And now -3, of course, is not a positive exponent, so we have to rewrite this as 2 times b to the power of 8 over a to the power of 3. So for question C, first what we're going to do is we're going to expand the powers. So 3x to the power of -2 times y to the power of 4 all to the power of 2 is the same as 3 to the power of 2 times x to the power of -4 times y to the power of 8, which simplifies to 9x to the power of 4 times y to the power of 8. Now, if we were to rewrite this, we would have 9x to the power of -4 times y to the power of 8 all over 9x cubed times y to the power of -1. We can simply cancel out the 9's, which are the coefficients, and so we'd get x to the power of -4 times y to the power of 8 over x cubed times y to the power of -1. Now we're going to subtract the powers, so we'll get x to the power of -4 minus 3 times y to the power of 8 minus -1, which equals x to the power of -7 times y to the power of 9. And of course, -7 is not a positive exponent, so we have to rewrite this one as well, which gives us y to the power of 9 over x to the power of 7. So now for our final question, let's first expand the brackets again. So we have 2a to the power of -3 times b squared all to the power of 3 is just the same as 2 to the power of 3 times a to the power of -9 times b to the power of 6, which equals 8a to the power of -9 times b to the power of 6. Now we're going to multiply this onto the numerator, so it becomes 8a to the power of -9 times b to the power of 6 times 4a to the power of 5 times b to the power of -4. So with our coefficients, we'll get 32, since it's 8 times 4. And with our powers for a, we're going to get a to the power of -4. And with our powers for b, we're going to get b to the power of 2. Now we're going to divide this by the denominator, which is 8 times a to the power of negative 2 times b to the power of 3. So let's again divide our coefficients. So 32 divided by 8 is 4. Now let's divide our a power. So we have 8 to the power of negative 4 over 8 to the power of negative 2. So that's just negative 4 minus negative 2, which is negative 4, plus 2, which is negative 2. And now for our b powers, we do the same thing. So that's 2 minus 3, and that's negative 1. Now, of course, negative 2 and negative 1 are not positive integer exponents. So we have to rewrite this as 4 over a squared times b. Let me know how you did in the comments, and next we're going to be taking a look at rational exponents.